Hi, this is Jake Montgomery, and I am working on problem 3 of homework 1. This is the video assignment for it. And problem 3 tells us that we have an isolated system of free, non-interacting particles. Firstly, right there, non-interacting, essentially, in this case, would mean non-colliding particles. So we're not worrying about collisions and the effects that those collisions may have on the momentum or position on the particles. So they're not free and non-interacting, and they're moving in one dimension with momentum p and position q. Each particle is confined in a one-dimensional box with perfectly reflecting walls located at q equals -1 and q equals +1 in arbitrary units. So then it tells us to draw a square box of unit sides in the phase space, which is the PQ plane. As you can see, I've already drawn what it's told me to in this first graph here. So we've got the PQ plane, the phase space, and we've got a box spanning to +1 and -1 on all sides. So it's a square, essentially. Then it tells us to draw a square of sides 1/2 in the upper left corner of the box, as you can see right here. And this box occupies particles uniformly. And this would be our initial condition, as the problem gives. So all the particles are starting in this upper left corner of the box in our phase space. It's asking us what the accessible part of the phase space is, i.e. the region that the particles can occupy through evolution from the initial condition. So essentially, it means that in this box, these particles are all in a negative position because they're on the negative q side of the q axis. And on top of that, they all have a positive momentum, which means that initially they will all have a positive momentum, which means they'll be moving in the positive q direction. So they'll be moving from left to right. And it says these walls are perfectly reflecting, so which means they'll travel towards the right here, towards the positive q side, and then they will bounce off of this wall. They will reflect off this wall. Once they do that, once they reflect off of this wall, they will then have a negative momentum, right? Because they'll hit the wall, and then they'll be going the exact opposite direction with the same velocity that they had before, just negative this time instead of positive. So when they have a negative velocity, they'll have a negative momentum, which means in the phase space, once they get to this side, once they hit this q wall of the box right here, they will then immediately go to this bottom right corner of the phase space because that indicates a shift in momentum to negative, which I just discussed. They will then have negative momentum. So then once they have negative momentum, they'll have that negative direction again, and they'll start going towards the left side of the box because of the negative momentum and because it reflected off of the wall. So now it's going the other way. So then once it goes the other way, gets all the way to the other wall, then it'll bounce off the wall and have a positive momentum again, and then we'll end up where we started off if we're just tracking one particle. And the entire group of the particles will do essentially the same thing. However, it doesn't specify if they're moving at the same speed or different speeds. So that's why I just, am giving an example of tracking one particle. So essentially, the accessible part of the phase space would be what you see below here, where the striped region is the accessible part. So it'll basically make a box of on the top part of the box and the bottom. So it'll make two regions in the phase space here that the particles can occupy. So, yeah, and since it's perfectly reflecting, there wouldn't really be any momentum below a magnitude of 1/2 because all the particles started with a magnitude of momentum above 1/2. So that's number one. Number two says, consider how the shape of the distribution changes at regular successive time intervals. How does the distribution look after a very long time? So this is essentially referring to the second law of thermodynamics, where if you have an isolated system, the system starting from any initial condition will strive to achieve thermal equilibrium, meaning that the distribution of particles will be more or less homogeneous as time moves forward. So after a long period of time, a very long period of time, the particles should be equally distributed in the accessible region of the phase space. And that concludes problem 3 for homework 1. I hope you enjoyed my explanation. Let me know if I need to work on anything, and I will see you for the next homework. Thanks.